So last time we were doing optimization, which was mostly the states. So neural network has two components, right? The weights, or it can be written as J, W, or there's another T, and the nodes as S, V, or yeah, something else. Last time in the optimization, this portion was fixed. This was fixed. The only variable was S and V. That was optimization. Today we'll be doing learning, where even the W or the weights will also change, and the states will obviously change because that's the state dynamics, right? So I'll just first say like what all we'll be covering in this 1 hour. So we'll start with 1982 Hopfield's paper on the network, Hopfield's network, which is essentially, he termed as content addressable memory. Then we'll discuss some of the drawbacks that it has. Then we'll go to 1985 Boltzmann machine, which was formulated by Ackley, Hinton, and Sejnowski. Then we'll jump to 2002, which is again Hinton, which something called a restricted Boltzmann machine. And then 2006 we'll look at autoencoder or deep belief networks. Is my handwriting visible by everyone? All right. Right, so that's the plan, and so I'll try to finish it by within an hour. So let's just start with Hopfield networks. So Sitabra's talk, he touched upon Hopfield network, which is essentially you have certain states that you want to store, right? So alpha denotes, so there will be two scripts. So V alpha is essentially V1 alpha, V2 alpha, V3 alpha, and so on. If there are n nodes, then it's V n alpha, and alpha varies from 1 to p. So you're storing p patterns in a network of n nodes, right? So Hopfield gave this one-shot learning scheme, which is if you assign the weights as alpha V alpha equal to 1 to p, V alpha I, so this is I j, and V j alpha, right? This was the learning scheme that he proposed. Then you can show that these patterns will be the stable states of the network. So P is the total number of patterns being stored. Oh, I'm sorry. Can you just please come front? Because it's I mean, this is my handwriting is always pretty small, as most of my friends know, but yeah. So and the dynamics, so this is the weight update rule, so that's how you specify the weights, and the energy of the system is given by the normal Ising Hamiltonian, right? So energy of the vector of the state of the system in state V vector. So V I W I j V j. There are bias terms as well, but for now this is like trivial addition, so I'll just not consider this, but it can be easily incorporated. All right. So the system does normal Monte Carlo Gibbs sampling, whatever you like, and tries to go towards the minima of the energy landscape, right? And so we saw this, if you have this sort of a description, then individual nodes update using the sigmoid, right? So sigma of sum over I j not equal to I W I j V j, right? So this is the input received by the ith neuron, and it fires if it's above a certain threshold, right? So Hopfield actually, what he did, he didn't use a sigmoid. What he did instead, he used a step function, right, with a certain bias theta I. But in this case, we're not considering bias; it's okay, 0 or theta I, right? But if you incorporate temperature in it, then your sigmoid, your step function becomes a sigmoid, right? Okay. So that is one extension which Hinton and others and other StatMech people also realized, that if you introduce temperature, then you can make it probabilistic. The other thing that we saw in Sitabra's lecture is that there is a critical number of patterns that you can store. If you have a system of n neurons, then there's a critical number of patterns that you can store. There's a particular number of patterns which you can store, which is given by alpha Cn, where alpha C is around 0.134, as Amit Gurfin and Sompolinsky analytically calculated, right? So you can see that there is an upper bound to the number of patterns that you can store in a Hopfield. So in 1985, Hinton, Ackley, and Sejnowski came up with the Boltzmann machine, where their argument was simple. Here you have n neurons, and all the neurons are part of the visible, or all the neurons take part in storing the pattern, right? What Boltzmann machine does is, if your pattern is of size n, right? So you have n v, let's say n v is the number of neurons that are storing the pattern. So you're storing patterns which are of this form: v alpha equal to v1 alpha dot 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 v n v alpha, right? Alpha is going from 1 to p. So you're storing p patterns, and each pattern has nv number of neurons. Is that all right? The two indices, one is enumerating the number of patterns, the other is enumerating the spin or node or neuron, whatever, right? So what Boltzmann machine does is, it considers some extra neurons, nodes, called the hidden nodes, which I'll denote by NH, which sort of help in storing the patterns in this visible layer in NV, right? So you see what's happening. The total number of total number of states that can be stored now becomes PC is equal. So it was given by this, right? Alpha C equal to alpha C into n, right? So right now it's alpha C into NH plus NV, right? This NV was this n in Hopfield, because it was like the system size is the size of the pattern being stored. But introducing NH, you don't have any upper bound anymore, right? You can put as many hidden nodes as you want. So technically you can store as many patterns as you want. So Boltzmann machine gets rid of the capacity problem, right? Now in case of Hopfield's network, what he was doing is, he was storing certain states, which he was storing specific states, right? So if we look at the state space or probability of the different states being obtained, so I'll be switching between S, V, and that's why I wrote it down before that. PC, yeah. So in case of Hopfield, PC was given by alpha C into n. N is the system size and the pattern size. But in case of Boltzmann machine, it's alpha C into NH plus NV, and NH is unbounded, can be unbounded, yeah.
So what's the point of hidden if it is like, if we increase the number of nodes in normal Hopfield network, would we say that terms of network?
How will you do that? So let's say you're trying to store this, right? So you have a specified number of neurons. So how can you change the neurons if the number of specified neurons is fixed? Like number of neurons, like all of them participate in the pattern. Okay, so there is a, like, you can do something, which you can create replica or copy. So instead of v1 alpha, you have v11 alpha, where v11 alpha takes the same value as this, but I'm not sure if that will work out. But you can essentially increase the system size by making degenerate spins. but I'm not sure if that will work out. All right. So what Hopfield was considering was particular fixed states, right? That is, in the state space, they're like delta functions, right? So they were storing S1 vector, S2 vector, S3 vector, and so on, right? Now, a generalization that in Boltzmann machine that Hinton, Ackley, and Sejnowski did was, instead of having like a delta function peaks at different state vector values, you can consider it to be a probability distribution, right? So instead of S vector, what I'll write here is P of V. Oh, okay. So this is in the visible space. The hiddens do not care. So that's why I just want to specify the visible. So I'll probably write SV, right? So in this visible space, you're storing, instead of delta function like particular states, you are storing a distribution of states, right? That's one of the jumps they made. So Hopfield gave a one-shot learning algorithm, which is essentially this, right? Okay, to get an intuition, I should have showed this. Hopfield's one-shot rule can actually be seen why it works, right? You can very easily see it. So this is the learning rule, right? So people who are not aware of Ket-Bra notation, this is essentially a column vector, and this is a row vector, right? So if you multiply it, so this is n by 1, this is 1 by n. So your W becomes of size n by n, right? Now realize, yeah, so this is that fine? Yeah, okay. So then what is the energy of a particular state V? It's given by minus half V, right? This is a row vector, right? W V, right? It's essentially the same thing. Over here I'm summing over the indices separately. Here I'm not summing over the indices separately, but considering a Ket-Bra notation, right? Inner product. Open up the W. If you open up the W, yeah, V alpha are the patterns being stored, right? Take out the sum over alpha outside. You see, it essentially becomes V alpha inner product whole square, right? It's okay, right? What I did here, it's column vectors and row vectors, and since W has a column vector into a row vector, put the summation outside, and I can collapse this, right? I can collapse this as well, and so I have V inner product V alpha, and now I think you can see that when V is equal to V alpha, right, they're the same. If they are the same, if both of these are the same, then you get n, which is the maximum value that you can get, right? So I hope you can appreciate the fact that this will give you the least energy when V is equal to V alpha. When V is not equal to V alpha, you have terms cancelling out and the energy will be higher. So this was this beautiful intuition of Hopfield, and he came up with this one-shot learning rule, right? But that is one-shot learning rule. How can you learn a probability distribution with a one-shot learning rule? You can do continuous sampling and then do it, but instead what Boltzmann machine does, or what Hinton proposed, is instead of doing a one-shot learning rule, is there any way to compare the probability distributions, right? So what are we doing in Hopfield network? We are storing the states, we are constructing the energy landscape such that the minima of the energy landscape correspond to the stored patterns, right? That's what we saw. EV becomes minimum when V is one of the V alpha. Yeah. So is there any way to make the minimas such that in Boltzmann machine you also do that, and so if we consider the energy landscape of the Boltzmann machine, we want it to be something like this, right? So the minima here will correspond to this observed state. So this is energy, and probability is like, if it's, you see it, then it's positive, right? Higher probability, and higher probability means lowest energy, right? Because the state is being stored. So this, we want to construct a system such that this matches and this matches with this, right? So what one can do is what Hinton and others did was they took the Kullback-Leibler divergence of two distributions to as the learning rule. So I don't know if you're aware, like, this gradient descent, right? So you change the W's in the direction of decreasing cost, and so what they proposed is treat C as dkl, Kullback-Leibler divergence of P E N V P E Q B. I'll say what these are. First, let's get what dkl is. So if you have two distributions, right, the dkl is given by P1, P2, okay, I should have, okay, doesn't matter, V alpha ln of P1 V alpha by P2 V alpha. So this is the Kullback-Leibler divergence, and you can get a sort of a feeling out of it, right? So if so alphas are the different points in the state space or in the support, whatever you call it, and so you're looking at the probability of getting V alpha of distribution P1 and P2, right? So if P1 is equal to P2 for a particular V alpha, then ln 1, which is 0, right? So that gives a 0 contribution to the DKL. But whenever they're asymmetric, you get a contribution to the DKL. So DKL will be 0 only when the P1 distribution is equal to the P2 distribution. If there is any offset, you get a positive value, right? So
What is it called? DK?
Kullback-Leibler divergence. Kullback, I don't know. This is one of the ways in which you can sort of compare two distributions, like find the distance between two distributions, or how far apart they are.
So what is the 2 bars?
Which 2 bars? So here we are comparing two distributions, right? So they generally put 2 bars as a notation.
I mean, this is like, what is the difference between these two distributions?
Yeah.
Can you explain
With-
gradient descent part? So data of the return.
Right. So you have something like this as a cost, right? So this is your state space, this is your cost, right? So if you're somewhere over here, where will you move? How will you move? You will move in the negative gradient of the cost function, right? That's what we are doing. So that's why it's called gradient descent, because you're descending down the gradient. It's actually, yeah, what?
Scale divergence, like helping us to
So scale divergence is the difference between, like, the distance between two distributions, right? So we can treat it as, so what do we want? We want the P1 and P2, P and V P equilibrium, I'll come to that. We want them to be equal, okay? So if we get them to be equal, then the environmental data becomes equal to the equilibrium data. Like whatever distribution you have from the equilibrium is actually mapped to the sampled distribution, right? So that's why we are treating DKL as the cost, so that it goes in the negative gradient of the cost, right? Okay. So what is PENV, PEQV? What it is essentially PENV is it says environment or sampled. So this is the probability distribution of the sample that we want the system to capture, right? So that's why it's called environment, like whatever you're getting. And P equilibrium is essentially you let the system run on its own free will, not free will, but in its own landscape, and it will give you a particular distribution of states, right? That is the P equilibrium, P equilibrium of the state, of the landscape, right? So these are the two things that we are comparing, right? So what they did is, okay, so another thing is the difference between Hopfield and Boltzmann machine is now our energy function looks a little different. Not little different, it's the same, but it has three components, right? One is connections inside the visible layer, right? So I'm shifting to this Vi and Hj notation, right? V and H. V means visible, right? So the patterns that we're trying to store, or not patterns that we're trying to, or the the layer, the size of the patterns that we are supposed to store, or the neurons where we are storing the patterns. So V, that is Vi, and hidden as the hidden part, right? So Vi Wij Vj minus half. So this is inside the visible layer, right? This is inside the hidden layer, and then you have a final term which is visible and hidden connections, right? Is that clear? So you can imagine the W matrix to be something like this. It's you have this part where it's W, VV, so connections going from V to V, connections going from V to H, connections going from H to V, sorry, H to V, connections going from V to H, and then connections in HH, right? So this is the energy, right? Right. So, and we know that so probability of equilibrium of a particular state, right? So S is sort of here I'm treating S as a concatenation of V and H. So V and H put together is the S, the state of the system, all of them together, right? So probability of a state is given by minus eta. So beta is obviously there, 1 by kBt, but here we'll just take it as constant. Energy of S vector by Z, normalization constant, partition function, whatever you want to call it, right? So that's P equilibrium S vector. Now if you treat this as a cost function, what will it look like? Dou Wij, so delta Wij is equal to minus eta dou Wij of dkl, right? P environment, P equilibrium is equal to minus eta dou Wij. If you open it up, then it essentially becomes sum over alpha P environment V alpha. Okay, V, I'm writing it V over here, this should actually be S, but okay, never mind. I suppose you'll get it. Right? So that will be my gradient descent for this Boltzmann machine, right? P environment V alpha does not have any of the parameters, W or bias, it does not have any parameters. There is no Wij inside P environment V alpha. The only the only place where it is in P equilibrium through this, the E, right? This E has theWij's, right? So this is the only term which will get differentiated. So you can move the dou Wij inside and work on it. I'll write an intermediate step because it's a little bit of a lengthy calculation and you can actually do it. It's a very conventional calculation in StatMech where you normally take the derivative of the partition function. So this will become eta sum over alpha p environment V alpha by p equilibrium V alpha dou wij p equilibrium V alpha, right? It can go inside, you do a derivative, this goes outside, and so you have equilibrium at the bottom, and then it's a dou wij of p equilibrium, and it becomes a square, and so it cancels out, and you'll be able to show that it comes out like this, right? Here, if you do the derivative, just realize that environment does not have wij. Only equilibrium has wij. Do the derivative with with keeping that in mind, and you'll arrive at this. And now if you open up the p equilibrium, so realize that z also has your wij, right? Normalization constant, right? It also has the wij. So if you do the derivative over here as well, you will arrive at, so delta wij equal to this. So delta wij equal to eta into sum over alpha if you do this calculation, you will arrive at this. This term is coming from this part, and the next term is coming from the bottom, and which is essentially eta of. So I shifted to SISG because it can, delta wij can be either visible hidden or visible or hidden, right? So SISJ of environment. So you sample when the environment is fixed, and you sample at the equilibrium of the system. So you arrive at this sort of a learning rule for the weights. What it actually, so operationally, what does it mean? What it means is you take the particular p environment V alpha, whatever you have, you fix it, you just clamp it or hold it to the visible layer and let the rest of the neurons evolve and reach their minima. This is some modified minima, right? Because here you are fixing it, so this is not the entire system minima, right? This is some sort of a driven minima. So once it reaches the hidden reaches the minima, you take the pairwise the statistics. You take the statistics. So this is environment clamped. So that's why it's given by this. So it's environment clamped statistics you take. Then you remove it. Then let the system evolve again, reach its new minima. It reaches a minima. It will reach a minima because it's a conservative system, right? So if you have low enough temperature, it will reach a minima. So once it reaches its own system minima, you take this pairwise statistics again, right? And so this was the first, like this was the rule which could in a sense learn these sort of machines. Now what turns out to be a bit difficult, it turns out to be a bit difficult because the visible still has hidden nodes inside, and so what? The visible has connections inside, and the hidden nodes also have connection inside, right? So there will be conflicting constraints, and that's why it becomes a little bit difficult for it to converge, for the system to converge. All right. Let me just see if I need to mention anything else. Yeah. Any questions till this point? I know we're going very fast because we're going from 1982 to 2006 in a matter of 45 minutes. So obviously we'll go fast. right? So if you have any questions, you can ask now or you can ask me later as well. So this is what we reach at, and turns out it's difficult to learn. So not a lot of not a lot of headway was made after that in Boltzmann machine, but in 1986 someone called Smolensky came up with something called a harmonium, which was essentially a bipartite graph. Everyone knows bipartite graph. Bipartite graph essentially means that connections run across layers. There are no connections inside a layer. So if you think of this structure, there are connections everywhere, right? Now, what harmonium is essentially, you strip out all the connections inside the visible and all the connections inside the hidden, and just keep the cross connections. So you arrive at an energy function which looks like right, and people saw that this sort of behaved well, but it wasn't that I mean, reaching an equilibrium in this one also turned out to be a little difficult, right? So let's just try to get a little bit of a feeling for harmoniums, which later was called a restricted Boltzmann machine by Hinton. So if you consider, so this is a layer, right? Hidden layer. This is a visible layer. No connections inside each of the layers. The connections are running across, right? So how will the states update? So you have probability of the configuration of the system can now be written as instead of probability of S vector where V and H are all there, we can sort of write it as V comma H as a joint distribution, right? So this is essentially e to the power minus e. Too many e's everywhere. Let me write specifically which one is what. Well, this is actually everywhere, this form. So this is the RBM energy. Where Z is sum over all V and H, right? Sum over H, sum over V, e to the power minus e RBM, RBM VH, right? So that is the probability with which you select a particular configuration V comma H. So what will be probability of V? So you sum over all the H and you arrive at, I'm leaving out the RBM because you already know what it is, and by Z, right? Now realize one thing, all the nodes here are connected to only the visible. All the nodes in hidden are connected to only the visible, and all the nodes in visible are connected to only the hidden. Yeah. So probability of V, let's say I, given a particular H vector, right? So probability of a particular node here given the H vector will not depend on the V at all. It will not depend on any other V. It will only depend on the H, right? So it can actually be written, sorry, the normal stuff that we have been doing. Right? And since they are connected to only the cross ones, you can write the total probability of all the probability of getting an entire visible vector as a product because they are independent, right? If the probabilities are independent, you can make them into a product, right? So since they are independent of each other, you can write it as a product, right? So I'll write it as PVI given H vector, right? So that's a jump. How? That's a jump in the learning as well and the system. How? In case of the Boltzmann machine, you are continuously doing randomly selecting nodes and updating them and hoping that it converges, but sometimes it goes up, sometimes it comes down. But here you can enumerate the sampling that you're doing, right? So you start with a particular visible vector, the environment visible vector. You can call it V0. It sends off, it activates the hidden layer. We can call it H0. That activates the next one, call it V1, and so on, right? And you can keep on doing this till the system does not evolve anymore, right? So it reaches the equilibrium. So here I'll write infinity, H infinity, since we can enumerate them, and theoretically it converges to equilibrium only at the infinite state if the system is very large. Yeah.
That's a conditional problem.
Yes. V given the H vector is set, right? So this is set. It's not changing. Yeah, you just update all the VIs, and that is absolutely possible, right? Because the VIs do not talk to each other, so it doesn't matter which VI you're updating first. So this is what is called alternative Gibbs sampling.
What is that? In a probability of Vi given H.
Yes.
What's after the equation?
Sigma. The activation function, or like the sigma, it's there everywhere. Like that's how the neurons see how much input they're receiving and decide on a probability with which they'll turn on or turn off. Yeah. How many people have I lost? Or how many people are with me? Oh.
But
Yeah, yeah.
conditional probability, how does it translate to that picture?
This picture. So this, very good, very good. And this will be PH0 vector given V vector 0. This pass. So, right? So this will, I mean, you pass it like with this sigmoid, and the activation is essentially this. So I shouldn't say PH vector over here, but this H0 is given a V0, and then it passes on to again. So this will be PV1 given.
H not tower property.
Whoa.
It's called tower property, like conditional. That is like you're just like.
I don't know any tower property.
As in, like, if you have a event dependent on the state, you just like break it up into a series of conditions. It's like, how do you say, like, breaking up the first condition into a series.
The first condition of so V vector, this is Vi, this is a particular node I. V vector is essentially all the VIs. It has all the VIs, so that's why it came out as a product, because they're independent of each other. Sorry, I think I don't get your question.
So, are they in sequence in the product? Are they like?
They don't have to be in sequence, they're independent of each other. I mean, yeah.
Like, so what is the conditional probability of the like, what is the probability of the
So here, there is a given H vector. I am evaluating what is the probability of a particular configuration of the V vector, given an H vector, which is essentially can be decomposed into individual of them. Right. Good. Okay. Right. Yeah.
We are representing a pattern of different layers, like layers.
There are only two layers, hidden and visible. This is the system going towards equilibrium.
So overall the pattern is two layers.
Yes, the given pattern is only invisible. Hidden is hidden. We don't know. We are not specifying the pattern in the hidden. The system will figure it out. Right? The visible pattern is the one that we are trying to, we are making the system learn.
No, but in the sampling, you're changing the H also like HIs.
Here?
Yeah. So
Yes.
here, which I takes the vector.
Yes. H is a vector. Well, I mean, both of them are like, combination of multiple units, right? So if you've ever come across like, neural networks, of this layer level structure, right? So this is like building a layer. Any questions? Any more questions? All right. So we arrived at this form for the Boltzmann machine, right? And you will realize that it's actually the same calculation. The only difference is P equilibrium V alpha. Instead of having these many W's, it has only one W. So there's not much of a difference. It will be the same thing, right? So the delta Wij, if you do that same calculation, will be eta Vi Aj equilibrium, sorry, environment minus Vi Aj equilibrium. Same spirit as that one, right? Here I can say Vi Aj separately because I have only one set of weight, which is the cross weights. Here I had everything connected, right? Right. Now realize because of this independence, we were able to enumerate the Gibbs sampling, right? So you can write it as Vi Aj 0 minus Vi Aj infinity, right? No. It's going towards the equilibrium, right? What do I mean by V infinity H infinity? It's like it's keeping on sampling till it reaches the equilibrium. V0 H0 is when it's the sample distribution, the distribution because of the sample. Yeah. So this is the same thing over here. Environment is the sample that the system is being given, and equilibrium is the same as infinity because it's gone to the equilibrium. Yeah. Right. So now as you can imagine, if the system size is very large, it will be very hard to make it converge, and so that's what people doing harmonium faced. That it was still quite difficult to huh? This. So you clamp it over here. You don't have to clamp it anymore. So you just put the vector over here, the visible vector or the sample data on this. You do one pass of the Gibbs sampling, you get a particular H. So this, the statistics obtained by taking V0 of this, like VI's of this, and HJ's of this, will essentially give you this. I mean, that's what it means by 0. Thanks for asking that question, right? So you're doing the statistics with this thing, right? You have this V0, the sample data, and the sample data activating the hidden layer, and that is your V0 VIHJ 0. VIHJ infinity will essentially be the statistics after it has reached its own equilibrium. So this will be the system equilibrium, and this is that clamped equilibrium, right? You clamp it and then you let it evolve, but here you don't need to clamp it because one pass itself it will reach the equilibrium because everything is independent, like all the nodes are independent of each other. So at one pass it will reach the equilibrium, right? All right. So yeah. In 2002, what Hinton did is he realized that instead of doing it till infinity and making the system go towards the equilibrium, you don't have to do so far. It's enough to just do it for one pass. So this sort of a learning scheme, he didn't theoretically show it, he empirically showed it, that this sort of a learning scheme is enough as a learning signal for the system to learn the patterns in the V vector, in the patterns provided in the V vector, right? So you don't, so that increases the speed of learning tremendously, because you don't have to make the system go to equilibrium at every step and then take the difference between the pairwise correlations and then learn the weights. You can just do it one pass, done. In theory, one pass, but the more you do, the faster it descends. But one pass is good enough. And he called it contrastive divergence. So that was Kullback-Leibler divergence. He called it contrastive divergence because what he was doing is essentially he was taking the difference of two Kullback-Leibler divergence. So P0, P infinity minus dkl P1, in this case it's P1, P1, P infinity. So he called it CDK, where the 1 is replaced by k. So you do k number of sampling, right? This looks like an x, this is a k, right? Contrastive divergence. So you're contrasting the two, these two Kullback-Leibler divergence, right? So he saw that once you do the derivative, like do the same thing, like delta wij is equal to minus eta dou cd dou wij instead of dkl, right? You arrive at sort of a same learning rule, like you can take this out, but you still have a small contribution. But empirically he showed that it's negligible. It doesn't, like, most of the time it's in the same direction or it's negligible. Yeah, and with that, what came into being was a restricted Boltzmann machine. So you have two layers, hidden layer, visible layer, learned. So this is your V1 H1, right? So this will be your V1 H1. And yeah, that's how you can like learn this Wij's using the contrastive divergence, right? Yeah, so that was RBM in 2002, and but there was no way to, they couldn't really find a way to make a bigger network using this sort of a rule. That is, if they start with, let's say, a 3-layered network, there was no way of learning the weights. And in 2006, Osin Deroute, I think a PhD student of Hinton, what he realized is, why do it at one go when in step 1 you learn a weight, right? In step 1 you learn a weight, 1 RBM, you learn this weight using the RBM. Step 2, you take this hidden layer activity as a visible layer and then learn the next layer of weights, right? So RBM used to make this layer, then again another RBM used to make this layer, and you can keep on doing it, right? One on top of the other. And that was shown in 2006, and like I think there were a couple of things. They made something called a deep belief network out of it. They made something called an autoencoder out of it, where so you can have multiple sort of things, right? Here most of them are sigma, like sigmoid function activated. You can take linear function activated, or you can, so this is unsupervised classification, right? What you can also do is something like this, right? So you're passing something, and like in a test training sample, you know that you're passing a particular class, right? So you pass it and you say this is class A. So it can do supervised classification as well. And so that was in 2006. They made deep belief network and autoencoder. So I'll show you how the landscape looks like a little. Okay, so like graphically, the entire space looks something like this. You have v vector, you have h vector. So and the z axis out of the board, inside the board, whatever, that's the energy, right? So this will be the energy. So what it looks like is, for particular visible layers, like visible units, this is one of the patterns that you're trying to store. This hidden layers will store this pattern. Next, this one is being stored by this area, and then so on, right? And so what it does, as you can see, these are sort of like very flat. So you get a very you get a particular visible vector for a lot of different hidden vectors, and that sort of that we'll actually see with the RBM. Gayatri ma'am, how do I call her? Yeah, okay, yeah. Yeah, so that's essentially the energy landscape picture, where you have these visible layers. So the distribution looks something like this. You have, so the probability like of the distribution that you're trying to store has a peak here corresponding to this, has a peak here corresponding to this, and a peak here corresponding to this. So that will be your P of V vector versus V vector, and it's stored like this in the energy landscape with the help of the hidden, right? And the energy is given by the ERBM, the cross connections, right? So this is essentially energy minimas of RBM. So what I'm storing in the visible layer, so this is a single RBM, right? What I'm storing in the visible layer are these patterns, these 4 patterns. This is the node index. Oh no, I forgot to give the label, but this is the node index. This is the alpha index, like this VI alpha, right? I referring to the node, alpha referring to the pattern index, right? So I'm storing these 4 configurations in the RBM, right? Now what I did is I start from any random initial configuration in the RBM. So I put a random V vector, and then I do that alternate Gibbs sampling for a couple of times till it reaches an equilibrium. What does it reach to? It reaches to these vectors, these visible vectors. These are the visible vectors. I am not plotting the hidden vectors over here. These are only the visible vectors, right? So these are the configuration that it goes to. So this is index again, node index, and this is the pattern, like pattern index. So it collapses onto these many patterns, but you will see this pattern, which it okay, it's arranged according to the number of times it has converged. So the top ones have converged the maximum number of times. So you can see the top layer over here is exactly this. The second one is exactly this. The third one is exactly this. The fourth one is exactly this. Then the others, if you notice, there is probably a single, like there's one mutation over here. Then over here, there's one mutation over here. So these are very close by because of the temperature in the updating scheme. That's why you have these single flips, but they're still in a particular minima. They're just moving around a little bit, right? So in essence, you start from any random initial configuration, and it will go down to any of these 4 states. What is this? This is essentially the same thing. I trickle down the energy landscape after learning the weights, and these 4 are the energy values of these 4, and they occur at the first. So they it reaches the minima the most number of times. These other ones correspond to the other patterns. So one thing you can notice, this is the architecture of 1632. So the visible layer, the lower layer is 16, and the upper layer is 32, right? 16, yeah, 16. This starts from 0, that's why it goes till 15. So the architecture is 1632. Now you can see the 32 is actually, like in the secondary layer, you have a lot of different microstates, right? There are a lot of microstates. So you consider this particular one, right? There are a lot of different microstates for a single visible macrostate. So that's what I mean by these energy minimas having long ravines in the hidden space. Like in the hidden direction, it's very ravine like, so it can sort of go around and yeah, makes it more stable. So I've this is the 2006 paper which made the news, where they made something called an autoencoder, where you do this RBM like one by one on top of another, but at the end you put a linear unit, or you don't put it through a sigmoid. You just Wij Vj plus bias. You don't pass it through anything, and that the final layer is 2. like there are 2 units in the final layer, right? So you essentially get a 2-dimensional representation of your space, and you can see, so this is the what documents, searching for documents through queries, and it can very nicely sort of segregate out properly when compared to something called a latent semantic analysis. I don't know what it is. PCA, you have heard of PCA, like in Anindya's talk as well. So this is PCA on the MNIST data set. So it's essentially handwritten digit recognition. I think there are 70 or 80,000 digits written by random people, and it tries to learn the weights, right? So this is through a PCA, principal component analysis of that, and this is through an autoencoder. So you can clearly see that there is a advantage. Right. So I have given a shot on the symbols, and they don't look very good, but you can sort of see, like things sort of separating out like this over here. So this is I've given how many? I've gave it by 5, 700 by 5.
What were you trying to do here?
Same thing as an autoencoder. I have multiple layers of RBM. The final layer is a linear unit with 2 linear units of size 2, so that I can plot it on the x and y axis.
That is, but like, how do you relate that to the symbols?
So the symbols are what, 64 by 64, right? It's 64 by 64. MNIST data set 64 by 64, right? So you make it linear, 64 into 64, 4096, no? Yeah, 4096, and you feed it as the visible layer, and it's sort of so this machine is very good at doing higher order correlations, because the H's, the hiddens, are actually directly connected to multiple V's, right? So only if, let's say, a subset of V's are active, this particular H turns on. So it does very high order correlation. It's capable of doing, like arbitrarily high order correlations. So that's what is generally, like very, very nice about this thing. Yeah, so it doesn't look that great. I think one of my problems was I used I couldn't do it on a very large system. So in case of MNIST, there are 10 classes, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here there are 700 classes. So I need a really large hidden layer, and I suppose it didn't really work out that well, but I should give my thanks to Ashraf, and I don't see him. Ashraf for, like no, he's right there, and and Aniruddha. He spent from 11 in the night to 3 in the morning writing, like helping me optimize. I gave a talk on optimization my last talk was optimization, but I can't optimize my code. So he spent 4 hours optimizing my code, but yeah, big thanks to them. So, like final slide. This is I realized that the simulated annealing and the temperature, idea of temperature, was really, like, you guys got very interested in that. So I thought of showing it. So these are 4 in the symbols, and these are the 4 minimas. I mean, you cannot see them in it. I've constructed it like that. So for different temperature, the temperature goes in the state update rule, right? You have the sigmoid, right? And the sigmoid has a temperature in it, right? E to the power minus, so the denominator has a 1 plus e to the power minus energy by kBt. Kb is 1, T, right? So this is that T. So when the temperature is very low, you get the symbols perfectly. Increase the temperature a little, you get noise, right? Increase it too much, and it jumps out, and it's in the C. So with that, thanks.
You're much better at time management.
I skipped a lot of stuff. All right, yeah.
Any questions?